up to, we're going to be looking at 4 final states of the Higgs decays: all electrons, all muons, and a mixture of electrons and muons. So due to time constraints is not a tutorial with exercises you can try, but there are 10 such tutorials. I went back and looked in the modern era, which is awkward array version at least 1, and 5 of them even have YouTube videos. So so the value of this one to you is that this is live and you can ask questions and I'll answer them. The pre-recorded ones, that's not going to work. Also want to point out that there are HSF training events with Uproot and Scikit-HEP modules. And don't forget that all of these projects have their online documentation. And then these are the versions that I'll be using if you want to try to do this on your own computer, like after time. But if you're running it on Binder, you've got all the software already. Okay, so as an overview, just as in the broader Python world, the functionality in Scikit-HEP is provided by small specialized interoperating libraries that build on each other. So, so just as when you're doing an analysis, like in any scientific field, you'll be using some foundational libraries like NumPy, Jupyter, and such, as well as some very specialized libraries like SunPy if you're doing solar physics, and that sort of thing. In the high-energy physics world, we have the same kind of structure within that. There's the outside world where we're using a lot of these tools that are available across for all users of Python. And then we also have layers of foundational libraries and a little bit more specific to some very specific packages. And here I'll be talking about 4 of them. Uproot reads and writes root data as arrays. Awkward array manipulates arrays of data structures. Hist fills histograms from arrays of data. And vector transforms arrays of 2D, 3D, and Lorentz vectors. So if you've noticed, you know, all of these, we're talking about arrays. Using these effectively will require thinking about whole arrays at a time. And if you're coming from, say, the C++ world and doing a lot of for loops, then this will be new. But actually, this array at a time thinking is a programming paradigm, kind of like imperative program with the for loops, functional programming where you're passing around functions all the time. You saw some of that in Henry's talk. Array-oriented languages are another class of languages in which the fundamental data type is an array, and most of the functions operate on arrays. There are quite a few of these languages. As I learn about more of them, I add more of them on the timeline. They all go back to APL, which is one of the foundational languages from the 60s. Another interesting feature about just looking at all of these array-oriented languages is nearly all of them are interactive languages. So they're meant to be used from a command line or a notebook. 2 exceptions are Fortran 90 and Dex, which have array-oriented features, but are not usually used from a command line. So the reason for this sort of correlation between array-oriented languages on the one hand and interactive languages on the other, the fact that they usually go together, is because this mode works particularly well for studying distributions of data sets. So if debugging doesn't mean you look at a particular value and ask, why is this a 4 instead of a 5? If debugging means looking at a distribution saying, what's that weird peak over there? Then you need something to be able to operate on a whole array, look at it, operate on a whole array, look at it. And that's what these languages provide. So let's go with an example. Actually, what I should have done is evaluated these import statements so the following things will work. Okay. Right. So by way of example, let's start with a Gaussian data set. So it's a NumPy array, and you ask, how are they distributed? So there is a histogram function that will just show that. Then when you're analyzing this more, you're going to do some operations on your data, like squaring each point. And you ask, how is the square of each point distributed? And here we have the data set squared. We didn't have to write the for loop because there are syntactic structures for saying, if you say an array squared, you get the square of every value in the array. And you get a different distribution, and that's what you're interested in. You're interested in looking at some weirdo function because you're doing a lot of manipulations, and you want to know what that looks like. So like the shape of this last distribution would have been really hard to guess, actually. I put that together in something like, I know that it's going to go from -1 to 1 because I took the sine of it all, but how it's shaped inside of that can be pretty subtle to try to figure out what that is. And that's why you have to do things on the computer. It would have been hard to guess, but as long as we're in this mode of compute an operation, plot, compute an operation, plot, we can analyze what mathematical formulas do to distributions, and actually setting up a for loop for every one of these would be a hindrance, so it'd slow us down. So array-oriented languages and interactivity go together. If you don't like Jupyter, which we're showing all of these presentations in Jupyter, there are alternatives. You can use IPython on a text terminal, or I usually use the basic Python prompt, actually. Or if you're comfortable with an IDE, the IDE probably has features that let you interact with an ongoing session. And I've seen people use that to great, in a good way. What I want to argue against is if you're doing this kind of work, don't build up a long-running script by running the whole thing over and over until you've already figured out the details. If you don't take advantage of this interactivity, you're like giving up half of it. So now let's start talking about Uproot. Uproot is a re-implementation of root.io in Python. So that means it has no dependence on C++ root. You can use Uproot without having installed root. And where this comes in useful is maybe you've got 2 or 3 installations of root, all different versions, and you need them for different projects. Uproot will let you open up a file without having to be in one particular environment or another. So it loosens some constraints. So these diagrams are sort of showing dependence. If you've used PyRoot, that's sort of built into root, and it sits on top of C++ root. If you use root numpy, that's a separate package from root, but it's also built on top of root. It needs to compile into a particular root, and if you're using a different root, it won't work. That's actually why Uproot came from conversations with the root numpy developer about what was working and what wasn't working. That's why Uproot is a separate development. So it's built on some things in the Python library, like in the Python ecosystem, like libraries for decompressing the data that might be in a root file. It's built on NumPy and Pandas and Awkward Array. And then things like vector and hist and coffee and your analysis scripts would be built on top of that. And it really is focused on just root.io. So the idea is that each of these packages is going to be focused on one particular thing. And that's why we want there to be projects like Uproot Browser to build on top of Uproot instead of all this being in Uproot. So let's see what an analysis would typically look like. Well, first of all, you have to find your file, and either you do that outside of Python, or if you are in Jupyter, you can use ! to run like ls to try to find the file. All right, so we found it. Now let's open it in Uproot. File equals Uproot open, and you give it the path. And if this is a remote file, root : / or https : / to wherever the file is located. And notice that in a good script, when you later turn this notebook into a well-defined script, you would put file opening inside of a with statement, the context managers that Henry showed. But when you're interactively exploring, you want the file to not be closed. You want it to stay open so you can play with it. So what's in the file? The file pretends to be a dictionary with keys and values. And since values would open all of the objects, usually want to just look at keys. So, so keys is, it's showing that these are the names of all the keys in this one. This only has one object in it. What kind of objects is that? This class names is an uproot addition. Normal dicts don't have this, but this is so that you can see for each of your keys, what is the type of object that is. So you can distinguish your T-trees from your histograms. So now, just like a dict, you actually open that by using square brackets and the name of the key. Now, you might be wondering, what's this :1? Oh, sorry, the semicolon 1 that I didn't have to write here in order to get the tree? That is a cycle number. It's a root thing. Root can have multiple objects in the same directory that have the same name as long as they have different cycle numbers. So you only use it to disambiguate if you really need to. So it's optional. So now this T-tree object is not all of the data. All of the data might be, gigabytes large, and you wouldn't want to just load it all into memory without getting a choice about what you want to load into memory. So this tree object is just the metadata, things like knowing the number of entries and knowing what T branches are in it. There's a interactive method here called show, which just shows it as a table. These are all of the names of the T branches. These are their C++ types, and this is their uproot interpretation. And yeah, you can get all of this information programmatically. You don't have to parse the text of the show method. If you need these things, tree is acting like a dict, which has where you can get key value pairs by asking for items. And then this value is a T branch, and it has things like the type name and a whole lot of other metadata. So you can get all that information programmatically. So now let's actually read real data out of the file. So let's say we want to read the muon, PT, eta, and phi and charge into arrays. So we only want to get these columns or fields and not any of the others. You can do that by passing the names explicitly to the arrays function, and you can just look up the documentation for how exactly to do this. But here I'm just doing a walkthrough. So this returns the data as an awkward array, which I'll talk about in a little bit below. But first I want to clarify that this can take a long time if your file is large. So there are ways of preventing it from taking a long time. So you can set an entry start and stop, or just the entry stop, in order to not read out, what is this, 300,000 events, but instead just read out 100 events. All right, so this muon kinematics that we pulled out here, this is an awkward array. The default is for uproot to output awkward arrays. You can also have it output NumPy arrays when that's possible. For this file, that's not possible because these data, like the muon PT, in the first event, there are 3 muons with PT. The second, there are 0. The third, there are 0. The fourth, there are, I don't know, looks like 7. A NumPy array has to have the same size in each dimension. So, sorry, no, that's the right. The first dimension can have a different size from the second dimension, but all of the nested lists, all the way down the second dimension, all have to be the same size. You wouldn't be able to have different numbers of particles in different events if you're using just NumPy. So that's why we have awkward array, and then this is just turning it into a Python list so that we can examine a little bit of it. Only looking at the first 4 events, because turning all of it into a Python list would be slow and costly. Python lists and dicts are slower than array-based things like awkward array. Okay, so then there are also methods in awkward array, because now we've kind of left uproot. When we've got this muon kinematics awkward array, what we're doing with it are a bunch of awkward array things. Things like ask for what are the fields, and pull out just the PT field, eta, the phi, the mass, and the charge. Now, it's important to know the distinction between when you're reading things from uproot, when you say tree.arrays or branch.array, or tree.iterate. It's important to know the distinction between the uproot commands, which read from files, and the awkward array commands, which operate on this array that's already in memory. And that's what I'm doing here. We can ask, what is the data type? Data types are important to awkward array. This data type is 300,000 record structures with fields like muon PT, that's a variable length list of floats, muon eta, which is a variable length list of floats, etc. We'll be seeing a lot more of data types later on. And we focused down on the muon PT and asked for its type. It's just 300,000 variable length lists of float 32. Okay, so now back to uproot. Let's ask another question. We're asking a question of the metadata, this tree metadata. Which columns in the T-tree have anything to do with muons or electrons? So here, this is using the keys function like a dictionary, but uproot has additional methods as are arguments that you can pass to the trees function, to the keys function, such as filters with these glob patterns for taking everything that's muon underscore or electron underscore. So you can get the list, the metadata, the list of what these field names are, and then using the patterns that you've tuned to get the right list, pass those patterns to the arrays function and read just those. So you can test a filter name with tree keys and then use it on tree arrays. And that's a good way to deal with a large file. Here's a question. Does uproot read all the branches for all entries at the same time? This would potentially make the machine run out of memory. Yes and yes. It will read exactly what you ask it to read. And if you don't specify which entries, that will be all entries from the file. And if you don't have enough memory for that, that won't work. You'll get a memory error. That's why if you are memory limited or time limited, you can specify starting and stopping entries. Now you could use this function multiple times in order to carve up the file into chunks that you can read all at once, or you could do that automatically. There's another function called tree iterate, which makes a loop over chunks of the tree, and that's documented in the on the website, but also it's got a doc string. Anyway, oh no, that actually printed out the whole code for it. I think I only wanted one question mark. Okay, so back where we were. Yeah, so then this larger data set where I'm taking all of the muon fields and all of the electron fields, it has a correspondingly larger type. So this is where there's the potential for confusion between the fields of a T-tree that have not been read yet and the fields of an awkward array that have been read. And so that's just a distinction you want to keep in mind. They're named the same thing, Okay, so now moving on, let's start examining distributions with hist, and that'll be a step toward actually doing this analysis. So NumPy and Matplotlib both have histogram or hist functions, and these are display options. In particle physics, we almost always want a histogram, a histogram object. So whereas you can use Matplotlib like this to display this histogram. If you want to be able to make pre-book histograms in a booking step, fill them in a separate step, maybe fill multiple of them and add them together, and then plot that, you'll want to use the hist library. So here's making that same thing here. And now I'm realizing that it's 5 minutes before 10. Matt, does that mean that I've got 5 minutes to wrap this whole thing up?
Yeah, ideally.
Okay. There's a miscalculation on my part that we're not going to be able to get to that. Maybe it was
if you need another minute or two, that's okay, but we should try and start wrapping things towards the conclusion.
Yeah, sorry about that. This
it's okay.
It's not going to be able to do it in 1 minute.
Well, you don't have to do it in 1 minute. I mean, like, I understand that you want to take time for questions, but I think that if you can maybe finish things in the next 5 minutes, then we can maybe take like 1 or 2 minutes for questions and then go to the next talk.
I think what we're going to have to do is let's do all questions now, because I seriously miscalculated the length of time that it would take to talk through this. Could have been
no worries.
Ups at the beginning, or maybe I'm just talking too slowly. But there is a whole walkthrough here of going from this basic exploration that you've been seeing me do through making those Higgs peaks, and it's a great presentation. But let's just do questions instead.
Okay, great. Thanks very much, Jim. That was, even though we didn't get through all of it, I thought it was still quite excellent.
There's a second question here, which is, can you mention the distinction between PyRoot and Uproot? And yeah, so this is worth clarifying. PyRoot is part of root. And PyRoot provides 100% coverage of all the root functions. And it does it because whenever you are using PyRoot in Python, it calls the C++ function from root. That has advantages and disadvantages. The one very obvious advantage is that PyRoot can do absolutely everything that root can do. The disadvantage is that all of that reflection can be slow, and you wouldn't want to do PyRoot calls inside of a for loop if you've got a large amount of data. Also, this is, I mean, in part, this is all in the imperative point of view. You're writing for loops over these things. Uproot is only covers input and output. It doesn't cover it with the same function names as root does, and the interface is array-oriented rather than being imperative. So these are all differences, and so this is what you'd probably want to use Uproot if you want to just extract some data in order to use it in something in Python, such as one of the Scikit-HEP tools, or some machine learning projects, which usually take arrays as input. Even if you need to prepare those arrays with awkward array to turn them from jagged structures into rectangular structures. More questions. Is it possible? You know what I should do? I should just put this into the shared part of the screen. I did that. Oh, I'll check mark them. Okay. To read all the branches, I already said that. Is it possible to directly use Lorentz vectors instead of 4 individual arrays? That's unfortunately what I was going to show in more detail. That's what the vector library is for. And you can go through this offline to see how that works. Apart from being smaller, what's the advantage of reproducing root stuff into packages like vector? Would HEP be better served by contributing to root itself? So reproducing the root stuff in packages like vector, it's not entirely reproduced because it's a array-oriented way of doing it. So whereas if you are using like T-Lorentz vector in root, or if you're using the math Lorentz vectors from root, you'll be doing it event by event. And this is just a different interface to doing that, because you would write a function that would apply some vector transformation to all of the vectors in some big array, even if they're a jagged array of vectors. Would HEP be better served by contributing to root itself? I think that it's better to have a lot of these things in small packages. When everything is all in one big package that has to work together in a particular kind of way. And that way, the way that Root's philosophy for doing things is part of it is C++ first, and part of it is this focus on it's not very into loading a large array and just doing manipulations on that in memory. It's a lot more geared toward streaming through files. So it's a different point of view about how to do analysis. Is awkward the NumPy of jagged arrays? It is actually. There are other projects that are picking up jagged arrays, including some outside of high energy physics. And they are, some of them started with custom implementations of jagged arrays, and they're switching over to using awkward array. How is the C++ side different than NumPy? Okay, I've also seen some XML in awkward, but I haven't seen it in NumPy. Actually, okay, so there's a bunch of different questions. When you see XML in awkward, what you're seeing is it's not XML data, it's just a handy user view. I just thought that XML would be a good way of seeing nested data structures in text format on the screen. There's not actually any XML processing in awkward array. NumPy doesn't even come close to needing that, because NumPy has rectilinear arrays for which the structure is always very simple. So the reason for the XML is to try to express this nestedness. And that's really just for internal functions. The C++ side for awkward array and NumPy, they're not so different. They both do some C and C++ computations on the back end in order to provide but the primary focus is to provide a nice Pythonic interface on the front end. Also, by the way, awkward array uses NumPy a lot. Anything that NumPy can already do, awkward just uses NumPy to do it, doesn't replace it.
For time, we're probably going to have to go on to the next talk, but we can.
No idea what Pirate's going to do.
Yeah. But thanks again, Jim. This was really nice. And